How do you know if you are moving? If you've ever traveled on a train, you know you cannot always tell if you are in motion. Looking at a building outside the window helps you decide. Although the building seems to move past the train, it's you and the train that are moving. However, sometimes you may see another train that appears to be moving. Is the other train really moving, or is your train moving? How do you tell? Describing motion. Decide if an object is moving isn't as easy as you might think. For example, you are probably sitting in a chair as you read this book. Are you moving? Well, parts of you may be. Your eyes blink and your chest moves up and down, but you would probably say that you are not moving. An object is in motion if its distance from another object is changing. Because your distance from your chair is not changing, you could say you are not in motion. Reference points. To decide if you are moving, you use your chair as a reference point. A reference point is a place or object used for comparison to determine if something is in motion. An object is in motion if it changes positions relative to a reference point. Objects that we call stationary, such as a tree, a sign, or a building, make good reference points. From the point of view of the train passenger in Figure 1, such objects are not in motion. If the passenger is moving relative to a tree, he can conclude that the train is in motion. You probably know what happens if your reference point is moving. Have you ever been in a school bus parked next to another bus? Suddenly, you think your bus is moving backward. But when you look out a window on the other side, you find that your bus isn't moving at all. The other bus is moving forward. Your bus seems to be moving backward because you used the other bus as a reference point. Relative motion. Are you moving as you read this book? The answer to that question depends on your reference point. When your chair is your reference point, you are not moving, but if you choose another reference point, you may be moving. Suppose you choose the sun as a reference point instead of your chair. If you compare yourself to the sun, you are moving quite rapidly. This is because you and your chair are on Earth, which moves around the sun. Earth moves about 30 kilometers every second. So you, your chair, this book, and everything else on Earth move that quickly as well. Going that fast, you could travel from New York City to Los Angeles in about 2 minutes. Relative to the sun, both you and your chair are in motion, but because you are moving and with Earth, you do not seem to be moving. Measuring distance. You can use units of measurement to describe motion precisely. You measure in units or standard quantities of measurement all the time. For example, you might measure a cup of milk for a recipe, run 2 miles after school, or buy 3 pounds of fruit at the store. Cups, miles, and pounds are all units of measurements. Scientists all over the world use the same system of measurement so that they can communicate clearly. This system of measurement is called the International System of Units, or in French, Système International, or SI. When describing motion, scientists use SI units to describe the distance an object moves. When you measure distance, you measure length. The SI unit of length is the meter, or m. A meter is a little longer than a yard. An Olympic-sized swimming pool is 50 meters long. A football field is about 91 meters long. The length of an object smaller than a meter often is measured in a unit called the centimeter, cm. The prefix centi means 1/100th. A centimeter is 100th of a meter, so there are 100 centimeters in a meter. The wingspan of the butterfly, shown in Figure 3, can be measured in centimeters. For lengths smaller than a centimeter, the millimeter, or mm, is used. The prefix milli means 1,000th, so there's 1,000 millimeters in a meter. Distances too long to be measured in meters often are measured in kilometers, km. The prefix kilo means 1,000. There are 1,000 meters in a kilometer. Scientists also use SI units to describe quantities other than length. You can find more information about SI units in the Scales Handbook at the end of this book. Calculating speed. A measurement of distance can tell you how far an object travels. A cyclist, for example, might travel 30 kilometers. An ant might travel 2 centimeters. If you know the distance an object travels in a certain amount of time, you can calculate the speed of the object. Speed is a type of rate. A rate tells you the amount of something that occurs or changes in a unit of time. The speed of an object is the distance the object travels per unit of time. The speed equation. To calculate the speed of an object, divide the distance the object travels by the amount of time it takes to travel that distance. This relationship can be written as an equation. Speed equals distance over time. The speed equation consists of a unit of distance divided by a unit of time. If you measure distance in meters and time in seconds, you express speed in meters per second, or m divided by s. We would say that is meters per second because the slash is read as per. If you measure distance in kilometers and time in hours, you express speed in kilometers per hour or kilometers per hour. For example, a cyclist who travels 30 kilometers in 1 hour has a speed of 30 kilometers per hour. An ant that moves 2 centimeters in 1 second is moving at a speed of 2 centimeters per second, or 2 cm per s, 2 centimeters per second. Average speed. The speed of most moving objects is not constant. The cyclist in figure 4, for example, changes their speed many times during the race. They might ride at a constant speed along flat ground, but move more quickly as they climb hills. Then they might they might ride at a constant speed along a flat ground, but move more slowly as they climb hills. Then they might move more quickly as they come down hills. Occasionally, they might stop to fix their bikes. Although a cyclist does not have a constant speed, the cyclist does have an average speed throughout a race. To calculate average speed, divide the total distance traveled by the total time. For example, suppose a cyclist travels 32 kilometers during the first 2 hours. The cyclist travels 13 kilometers during the next hour. The average speed of the cyclist is the total distance divided by the total time. So to get the total distance, we take 32 kilometers plus 13 kilometers, which equals 45 kilometers. To get the total time, we take 2 hours plus 1 hour equals 3 hours. To find the average speed, you take the total distance of 45 kilometers and divide it by the total distance, which is 3 hours. And we get the average speed equals 15 kilometers per hour. So the cyclist's average speed is 15 kilometers per hour. Instantaneous speed. Calculating the average speed of a cyclist during a race is important. However, it is also useful to know the cyclist's instantaneous speed. Instantaneous speed is the rate at which an object is moving at a given instant in time. Knowing the speed at which something travels does not tell you everything about its motion. To describe an object's motion completely, you need to know the direction of its motion. For example, suppose you hear that a thunderstorm is traveling at a speed of 25 kilometers per hour. Should you prepare for the storm? That depends on the direction of the storm's motion. Because storms usually travel from west to east in the United States, you need to worry if you live to the west of the storm. But if you live to the east of the storm, take cover. When you know both the speed and direction of an object's motion, you know the velocity of the object. Speed in a given direction is called velocity. You know the velocity of the storm when you know that it is moving at 25 kilometers per hour eastward. At times, describing the velocity of a moving object can be very important. For example, Air traffic controllers must keep close track of the velocities of the aircraft under their control. These velocities continually change as airplanes move overhead and on the runways. An error in determining a velocity, either in speed or in direction, could lead to a collision. Velocity is also important to airplane pilots. For example, stunt pilots make spectacular use of the control over the velocity of their aircrafts. To avoid colliding with other aircraft, these skilled pilots must have precise control of both their speed and direction. Some pilots use the control to stay in close formation while flying graceful maneuvers at high speed. Let's go back and look at our tech and design and history. In 1818, national road construction. The speed of transportation has been limited largely by the quality of roads. The U.S. government paid for the construction of a highway named the Cumberland Road. It ran from Cumberland, Maryland, to Wheeling in present-day West Virginia. Travel by horse and carriage on the roadway was at a speed of 11 kilometers per hour. In 1885, Benz tricycle car introduced. The odd-looking vehicle was the first internal combustion gasoline-powered automobile sold to the public. Although it is an ancestor of the modern automobile, its top speed was only about 15 kilometers per hour, not much faster than a horse-drawn carriage. In 1908, Ford Model T passed production between 1908 and 1927. Over 15 million of these automobiles were sold. The Model T had a top speed of 65 kilometers per hour. In 1943, the diesel freight train. The diesel freight train traveled along the Atchison, Topeka, and Santa Fe Railroad, Arizona. Perhaps the most famous diesel train, the Zephyr, set a long-distance record in 1934, traveling from Denver to Chicago at an average speed of 125 kilometers per hour for more than 1,600 kilometers. In 1956, the Interstate Highway System established. The passage of the Federal Aid Highway Act established the Highway Trust Fund. This act allowed the construction of the interstate and defense highways. Non-stop transcontinental auto travel became possible. Speed limits in many parts of the system were more than 100 kilometers per hour. In 2003, maglev in motion, the first commercial application of high-speed maglev, which is magnetic levitation, was unveiled in Shanghai, China, during the 30-kilometer trip from Pudong International Airport to Shanghai's financial district. The train operates at a top speed of 430 kilometers per hour, reducing commute time from 45 minutes to just 8 minutes. Graphing motion. You can show the motion of an object on a line in which you plot distance versus time. The graph you see in figure 6 are distance versus time motion graphs. The time is shown on the horizontal axis or x-axis. Distance is shown on the vertical axis or y-axis. A point on the line represents the distance an object has traveled at a particular time. The x value at the point is time, and the y value is distance. The steepness of a line on a graph is called slope. So the slope tells you how fast one variable changes in relation to the other variable in the graph. In other words, slope tells you the rate of change. Since speed is the rate the distance changes in relation to time. The slope of distance versus time graph represents speed. The steeper the slope, the greater the speed. A constant slope represents motion at a constant speed. Calculating slope. You can calculate the slope of a line by dividing the rise by the run. The rise is the vertical difference between any 2 points on the line. The run is the horizontal difference between the same 2 points. So slope equals rise over run. In figure 6, using the points shown, the rise is 400 meters and the run is 2 minutes. To find the slope, you divide 400 meters by 2 minutes. The slope is 200 meters per minute. Different slopes. Most moving objects do not travel at a constant